Hello friends, welcome to my lecture series on digital signal processing. In previous lecture, we saw the Fourier series, which gives a spectrum of any periodic function in the form of orthogonal set of sine and cosine function. Now here, before we jump into Fourier transform, we'll see some important points about the Fourier series. The Fourier series can be expressed in trigonometric form as well as in exponential form. However, now onwards we'll see the exponential form of the Fourier series in various applications because it gives huge mathematical simplicity. However, in both trigonometry and exponential Fourier series, the basis function is a sine wave function, either in a trigonometric form or sine function expressed in a complex exponential. Now, why the basis function is a sine function in a Fourier series? Because the sine function with the fundamental frequency and its harmonics form orthogonal set of functions, that is, any two frequency components of sine functions forms orthogonal property, that is, the dot product becomes 0. So basically, the physical meaning of this is any two components are uncorrelated in orthogonal set of sine function. So one can interpret the Fourier series of any periodic function as decorrelation of correlated time domain function in a frequency domain, and hence this property is used in data compression as well. Another important property of sine function is it is a very smooth function. That is, nth order derivative of a sine function exists. In fact, infinite order derivative of sine function exists. And another important property is even if you take nth order or infinite order derivative of sine function, the output still remains sine function. Only there is a change in scale and phase, but it doesn't affect the shape of the function, and hence it is also called eigenfunction. That is, whenever a sine wave function is passed through any linear time invariant system, the output of the system remains sine function. Now, sine function can be also expressed in terms of complex exponent function using Euler identity, and that reduces the mathematical computation, which we had already seen in our previous lecture. When we talk about Fourier series in trigonometric form or exponential form, their spectrums are either one-sided or two-sided. Now, there is no much complexity in the graphical representation of the spectrum. Exponential spectrum, it is simply a mirror image of trigonometric spectrum due to the Euler identity, and amplitude is divided by 2. So this is a physical interpretation for trigonometric and exponential Fourier series. However, there is one important limitation of the Fourier series, that is, it is applicable to only periodic function, and this limitation can be overcome by applying some tricks which will generate a new formula which is called Fourier transform. Consider the concept of Fourier transform. So here we start with the exponential Fourier series, which is given by these two equations. That is, xt is a summation of exponential sine wave and its harmonics, and cn is an amplitude of the nth harmonic, which is given by integration of x of t e raised to minus jn omega naught t over the period minus t by 2 to plus t by 2. However, this equation is applicable to only periodic function. Suppose we have an arbitrary aperiodic function or a non-periodic function as shown below. How one can find out the frequency spectrum of such a non-periodic function using Fourier series? So it is a three-step process. Step 1, in which we'll convert non-periodic function into a periodic function with a period t by adding two pulses, one on right hand side and another on the left hand side. Now this function is called periodic version of the x of t, and it is indicated by capital T as a subscript in x of t. Now how one can obtain original function x of t from the periodic version of the x of t? So it is a very simple process. We have to make t infinity, that is shifting positive pulse to the infinity while the pulse on the left hand side is shifted to minus infinity. So mathematical formulation will become x of t is equal to limit t tends to infinity of periodic version of x of t. Now we can compute the Fourier series for periodic version of x of t using Fourier series formulation for x of t and Cn. Now here we are interested in the Fourier series of x of t and not periodic version of the x of t. So there we can apply the limits t tends to infinity and you'll get the expression for x of t is equal to Fourier series of periodic version of x of t where limit t tends to infinity. Similarly, we can obtain the equation for Fourier coefficient, that is a Cn, from periodic version of Cn, which is Cnt with limit t tends to infinity. And then we'll substitute formula for Cnt from Fourier series. Now here, as t tends to infinity, what is the impact on the spectrum of the signal? Now here, the fundamental frequency is omega naught is equal to 2 pi by t. So as t tends to infinity, fundamental frequency will start decreasing and it will approach to 0. Actually, approaching to 0 is not equal to 0 and hence it is indicated by a very small value d omega. Before we get into the mathematical application of this limit, we'll see the physical interpretation from the graph. So here, the frequency spectrum for some finite value of t as given by the Fourier series is a discrete in nature. Now as t increases, the fundamental frequency decreases, that is the spectrum will become denser compared to the previous value of t. Again, as t increases, the fundamental frequency will go on decreasing. And then one can visualize as t tends to infinity, the fundamental frequency omega naught tends to d omega, which tends to 0, and hence the frequency spectrum will become continuous in nature. So this is a physical interpretation of frequency spectrum of a signal as t tends to infinity. Now we'll apply this limit to mathematical formulae. Now here, as t tends to infinity, omega naught tends to d omega. Therefore, n omega naught tends to n d omega, which tends to omega. Now here we have to understand the point. N is a index which indicates a harmonic, while d omega is a infinitesimal very small value, and therefore the product n into d omega indicates that frequency exists for every value of omega, and hence n d omega will become a continuous variable omega. Now when limit is applied to this second expression, Cnt will become 0 because in this expression there is a term 1 by capital T and t tends to infinity, and therefore even though integration is finite, since t tends to infinity, the whole integration will become 0. This problem can be solved by shifting capital T on the left hand side, and therefore instead of computing limit of Cnt, we'll calculate limit of t into Cnt, which will become finite value, and therefore we'll get an equation for limit t tends to infinity t Cnt is equal to limit t tends to infinity integration of periodic version of x of t into e raised to minus j in omega t dt with limits of integration from minus t by 2 to plus t by 2. Now here, when you apply limit to each term of this integration, then limits of the integration when we substitute t tends to infinity, will become minus infinity to plus infinity. Now limit applied to periodic version of x of t from this formula will become your original function x of t. And as t tends to infinity, n omega naught tends to omega, and therefore it will become a continuous variable. So when you look at this integration, we are integrating with respect to time, and therefore time will disappear and we'll get a function of omega, and hence the entire equation can be written as x of omega, which will form the Fourier coefficient same as Cn. So we got a new equation for limit t tends to infinity t Cnt is equal to x of omega. So here we can write down x of omega is equal to integration of x of t into e raised to minus j omega t dt, which is called Fourier transform of any aperiodic function or a non-periodic function. Now this is a very simple and elegant equation which is the same as a dot product in a continuous time domain. Now we can find out formulation for x of t. So here again we'll apply limit t tends to infinity to the right hand side expression of Fourier series. Now here we have to apply this limit t tends to infinity to summation, where summation is with respect to n. N is a frequency variable which indicates a harmonic of a sine wave. Since omega naught tends to d omega and the effective value of n omega naught becomes a continuous variable, the summation will become integration. Now limit applied to Cnt, which we can obtain from this equation. So here limit t tends to infinity t Cnt is equal to x of omega. We can substitute value for t as 2 pi by omega naught, and when limit t tends to infinity is applied to omega naught, which becomes d omega, and this constant term move to the right hand side and then substitute in the equation. So you'll get a limit t tends to infinity Cnt is equal to 1 by 2 pi into x of omega into d omega, and it can be substituted in this equation, which will give the inverse Fourier transform. So here one can say x of t is a transformable to x of omega and vice versa. So inverse Fourier transform is also represents a dot product of x of omega with e raised to j omega t. Here e raised to j omega t is a complex conjugate of e raised to minus j omega t. That's the only difference between Fourier transform and inverse Fourier transform relation, and there is one constant 1 by 2 pi which is due to omega is equal to 2 pi f. So whenever it is integrated with respect to f, 2 pi will get cancelled. Otherwise both the formulations are nothing but the dot product of two variables. So this is an explanation for Fourier transform which overcomes limitation of the Fourier series, and it has a tremendous application in digital signal processing, and it also forms the foundation for Laplace transform and Z transform. In the next lecture we will see very important properties of Fourier transform, which will span a couple of subjects like control system, communication system, and various applications in the area of computer vision and artificial intelligence. I hope you must have enjoyed this lecture, and thank you for your patience and watching my show.